In the last lecture, we talked about communication via timing. And in this lecture, we're going to talk about another very basic modulation technique, which is communication using quantity. So in other words, the symbols that we're going to send they will be expressed in terms of the number of molecules emitted. So generally speaking, we've mentioned the possibility of a hybrid modulation scheme, but right now we're just looking at the pure modulation schemes. So while before we talked about timing, keeping the number of molecules the same, here we are going to vary the number of molecules and the timing of release will be held constant. So as I mentioned in a recent lecture about this, a couple lectures ago, sometimes this goes by the name of concentration shift keying. And it is relatively easy to accomplish if you don't have control over the individual release times of individual molecules. So in other words, one way to think about concentration shift keying would be you have your reservoir, and you have, for example, a door in the reservoir. And if you want to send a message, you open the door to the reservoir and let molecules flow out. So presumably you might not even have exact control of the number. We will generally assume here that you can control the exact number, but concentration shift keying could be accomplished by opening this door for a certain amount of time. So if you want a little, maybe you'd open it for a millisecond. If you want a lot, maybe you'd open it for 10 milliseconds. If you want 0, you just keep it closed. So concentration shift keying is used, in many demonstration systems. We'll talk a little bit about those demonstration systems at the end of the course, but this is basically because you can't control exactly the number of, it's difficult to control exactly the number of molecules being released, but it's relatively easy to do something like release or open a door or activate a spray that releases a random number of molecules and changes the concentration. So the techniques we're talking about are related to that, even if they're a little more refined than perhaps some of those methods. So let's talk here about the basic communication assumptions. So again, we're going to assume here, actually not again, we're going to assume here, recall that when we talked about timing, we were talking about absorbing receivers. Here, we're going to assume non-absorbing receivers. So a non-absorbing receiver in a 1D environment. So here's your 1D environment. It's going to be infinite in both directions. So the absorbing receiver, there's a point here, for example, at which the receiver existed. And so therefore nothing could progress beyond that point, because if it arrived at that point, it was absorbed. Here, my receiver, script R, the region of the receiver is going to exist here, and it's going to go from A to B, like so, where A is greater than B. So the receiver, R, script R, is a 1D region from A to B, where A is greater than B, and we're going to assume that both are greater than 0. Moreover, the transmitter, i.e. the molecule release point, is at the origin. That's right here. And we're going to assume, again, we're going to make this assumption that there's nothing else in the system except the emitted molecules. Two more things that we have to assume here. The molecules are all released at the same time. Similar to the last example, we're just going to consider like transmission of single symbols at a time. So without loss of generality, we're going to assume that the release time, TR, is 0. TR is 0. Just try that a little better. The receiver counts the number of molecules within R at each T. Otherwise, the receiver doesn't interact with the Brownian motions at all, and the molecules that are propagating don't experience anything different whether they're in the receiver or not. They just get counted. So what this boils down to, now remember from a few lectures ago, we talked a little bit about this. So what this boils down to is, what's the probability if I release a molecule times 0, and it arrives, and then I ask, what is the probability that it is within the receiver time t. So we know what this is. That's basically asking, what's the probability that the Brownian motion at time t is in R, given that the release at time of release, B of 0, is 0. Well, we also know that B of t is distributed Gaussian with mean 0. There's no drift here. I mean, you can easily modify everything that I'm talking about in order to take drift into account. So B of t is normal with mean 0, variance t. Sorry, I'm going to make that more precise. 2 dt, where d is the diffusion coefficient. 2d is then the variance, the fundamental variance of the Wiener process, and t is the time that's elapsed since release. So we can say that the probability that the Brownian motion is in the region, given the initial point is 0, that's basically, if you think back to our diagram, from A to B released at 0, then this is the integral from B to A of the probability density function of, sorry, let me actually make that more precise, f of B of t, dB of t. For convenience, for notational convenience, I'll let B of t equal x. So therefore, this is the integral from B to A, f of x dx, where x is a Gaussian random variable. So this becomes the integral from B to A of 1 over root 2 pi. The variance is 2 dt. So in fact, this becomes 4 pi dt e to the minus x squared over 2. Actually, it's 2 times 2 dt, so that again becomes 4 dt dx. Now, of course, as you're aware, this integral is not available in closed form, but we can solve it by defining special functions. And in fact, it will turn out that this is equal to, if you use the error function, it's 1/2 the error function of A over root 4 dt minus the error function of B over root 4 dt. So you can, if you don't like the error function, you can use your, it's possible to express this using your favorite defined function of the Gaussian integral. But this then becomes the probability of being in R. I'm going to give it this notation. It should be script R. Of T. So that's defined as PR of T, the probability that at time T, the molecule is in the region script R. So what we're going to do is we're going to say there will be a sampling time. TS. So in other words, what we're going to do is we're going to release the molecules at time 0. We're going to wait, and then at some time TS, we are going to sample R, and at that time, we count the number of molecules in R. So therefore, if we release a molecule, then the probability releasing, actually, let me be more explicit here. If we release exactly one molecule, the probability that it is in R at time TS is given by PR of TS. And you can go back to the previous page if you like. You can substitute TS in everywhere you like here. So substitute TS in there and there, and you get PR of TS. Okay. So how does this become a communication system? Let's consider the simplest possible expression of concentration shift keying. And it is basically on-off keying with one molecule. So if we want to send a 0, excuse me, let me back up. This is a binary communication system. If we want to send a 0, then we're going to send 0 molecules. If we want to send a 1, then 1 molecule is sent. Okay, so it doesn't get any simpler than this, right? So if you want to send a 0, you send 0. If you want to send a 1, you send 1. And we can analyze this very easily. What we're going to do, we are going to say that the probability, excuse me, let me back up. My observable Y is the number of molecules in the receiver time TS. So here is my region. There's my transmitter at the origin. Here is my region. And the idea is at time TS, I count the number of molecules Y that are in the region. There are different ways you could do this, but this particular way is relatively straightforward. Straightforward to analyze. So let's consider, sorry, I'm also going to say the bit, the transmitted bit. I'm going to call it X. So as in all communication systems, we need the probability of the outputs given the inputs. And what is that? So the input can be one of two things. So what's the probability Y given that the input is 0? Well, the output in that case can only be one of two things. There's only one molecule in the universe in this example. So the output can either be 1 or 0. So it is 1. Well, actually, excuse me, let me back up. In this particular version of the universe, there are 0 molecules ever. There's no molecules available because none are transmitted. X is 0. So what that means is that the output is Y. The output Y is 1. Sorry, let me back up. The probability that Y is 1 is 0. The probability that Y is 0 is 1. So in other words, we're guaranteed if we send nothing, we receive nothing with probability 1. On the other hand, probability of Y given X equals 1. Again, I can observe either Y equals 1 or Y equals 0. Now, now I know for sure that the molecule was sent. So therefore the probability that it arrived at time TS is PR TS. The probability that it doesn't arrive is PR, sorry, 1 minus PR TS. We can go further and calculate the probability of error. Which is very simple. So let's say the probability that x is 0 is equal to probability that x is 1, which is 1/2. In that case, an error occurs if I decide a 0 when a 1 was sent and I decide a 1 when a 0 was sent. We can see the decision rule over here very easily. If the well, hold on. So if nothing is observed, then we pick the greater of 1 or 1 minus PRTS. So we naturally pick x equals 0. Yeah, actually, let's make this more explicit. So the decision rule, maximum likelihood decision. So if y equals 1, then what do I have? Probability that y given x equals 0. That is the probability that y equals 1 given x equals 0. It's just given by this, it's 1. Correction. The probability that y equals 1 given x equals 0 is 0. And the probability that y equals 1 given x equals 1, y equals 1 given x equals 1 is PRTS. Which presumably will be greater than 0. If y equals 0, probability that y equals 1 given x equals, probability that y equals 0 now given x equals 0 is it's 1. Sorry, that's the wrong entry. It's 1 here and 1 minus PRTS here. So we have 1 and the probability that y equals 0 given x equals 1, 1 minus PRTS. So if y equals 1, I pick x equals 1. And if y equals 0, I always pick x equals 0. So that makes sense. If I see something, then I assume something was sent. If I don't see anything, then I assume nothing was sent. In general, these maximum likelihood decisions for concentration shift keying, if it's binary and if one of the output letters is 0, then if you see anything, you have to pick 1. Okay, so finally, probability of error. Now that we know how we're deciding, if an error is made if y equals 1 and x equals 0, or y equals 0 and x equals 1, because basically we decide x is the same value as y. So if we assume probability that x equals 0 is the same as the probability that x equals 1, which is 1/2. Then we get the probability of error is the probability that y equals 1 given x equals 0 times the probability that x equals 0 plus the probability that y equals 0 given x equals 1, probability x equals 1, which is getting a 1 when you send a 0, that's impossible. So it turns out this will be 0. The other term, the probability that y equals 0 given x equals 1, that's 1 minus PR TS. And the probability that x equals 1 is 1/2. So that is the probability of error. So this might have seemed like very basic analysis. This is an extremely simple communication system. In fact, what it boils down to is a binary asymmetric channel. That is to say that the probability of error given an input 0 is not the same as the probability of error given an input 1. In fact, because one of the two legs is error-free, this in fact turns out to be a Z channel. So the Z channel looks like if you have a 0, input 1, output 0, output 1. So if you input a 0, you can only get a 0, probability 1. If you input a 1, you can get either a 1 or a 0. So you can see why it's called a Z channel. And then I can write this. This is 1 minus PR TS. This is PR TS. So analysis of the Z channel is fairly simple, as you've seen. I just wanted to go through the example just to make clear that these systems aren't hard to analyze if you go back to first principles. Think about another case. What happens if, now suppose, if x is 0, I send 0 molecules again. If x equals 1, I send n molecules, more than 0, more than 1 anyway. Now what? So in that case, now the number observed at time ts, y, is a binomial random variable. And we saw this a few classes ago, a few lectures ago. We were talking about how when you're counting the number of molecules that end up in a region, it's naturally a binomial random variable. And in fact, we can write P of y given x is equal to, well, again, it's 0, correction. Actually, I'm gonna say it this way. P of y given x equals 1. So given that I sent something, that means that I must have sent n molecules at the beginning. Then the number that I observe at time ts is n choose k. PR TS, that's the probability of arrival at time TS to the power of, sorry, that's not K, that's Y. PR TS to the power of Y, 1 minus PR TS to the power of N minus Y. Moreover, if N is large, Y is approximately Gaussian. We talked about the mean and variance. The mean is now N times PRTS. And the variance is N times PRTS times 1 minus PRTS. So what you can do with that, if you come back and think about this analysis, your goal, as always, is to figure out if a 0 or a 1 is sent. So you can substitute those distributions back in here. Well, it wouldn't be binary anymore, but you would have the binary, either the binomial or the Gaussian distribution, and you would put them in here. You would develop your maximum likelihood decision rule just like this, and then you would be able to calculate the probability of error much like this. It does get even more complicated because now here we are only talking about binary transmission. There's in general concentration shift keying, you can do emery decisions, but I'm going to leave that up to you as an exercise. Hopefully you can see how to derive these kinds of relations and detectors using quantity as a form of modulation. And I'm going to draw this lecture to a close, and I'll leave the rest up to you.